Why doesn't add more cores face the same physical limitations as make the CPU faster? In 2014, I hear a lot of programming languages touted for their concurrency features. Concurrency is said to be crucial for performance gains. In making this statement, many people point back to a 2005 article called "The Free Lunch is Over," a fundamental turn toward concurrency in software. The basic argument is that it's getting harder to increase the clock speed of processors, but we can still put more cores on a chip, and that to get performance gains, software will need to be written to take advantage of multiple cores. Some key quotes. We're used to seeing 500 MHz cus give way to 1 GHz cus give way to 2 GHz cus, and so on. Today we're in the 3 GHz range on mainstream computers. The key question is, when will it end? After all, Moore's law predicts exponential growth, and clearly exponential growth can't continue forever before we reach hard physical limits. Light isn't getting any faster. The growth must eventually slow down and even end. It has become harder and harder to exploit higher clock speeds due to not just one but several physical issues, notably heat, too much of it and too hard to dissipate, power consumption, too high, and current leakage problems. Intel's and most processor vendors' future lies elsewhere as chip companies aggressively pursue the same new multi-core directions. Multi-core is about running 2 or more actual cores on one chip. This article's predictions seem to have held up, but I don't understand why. I have only very vague ideas about how hardware works. My oversimplified view is it's getting harder to pack more processing power into the same space, because of issues with heat, power consumption, etc. I would expect the conclusion to be therefore, we'll have to have bigger computers or run our programs on multiple computers. And indeed, distributed cloud computing is a thing we're hearing more about. But part of the solution seems to be multi-core architectures. Unless computers grow in size, which they haven't, this just seems to be another way of saying pack more processing power into the same space. Why doesn't add more cores face the same physical limitations as make the CPU faster? Please explain in the simplest terms you can. Smile.
Summary. Economics. It's cheaper and easier to design a CPU that has more cores than a higher clock speed, because significant increase in power usage. CPU power consumption increases rapidly as you increase the clock speed. You can double the number of cores operating at a lower speed in the thermal space it takes to increase the clock speed by 25%. Quadruple for 50%. There's other ways to increase sequential processing speed, and CPU manufacturers make good use of those. I'm going to be drawing heavily on the excellent answers at this question on one of our sister say sites. So go upvote them. Clock speed limitations. There are a few known physical limitations to clock speed. Transmission time. The time it takes for an electrical signal to traverse a circuit is limited by the speed of light. This is a hard limit, and there is no known way around it. At gigahertz clocks, we are approaching this limit. However, we are not there yet. 1 GHz means 1 nanosecond per clock tick. In that time, light can travel 30 centimeters. At 10 GHz, light can travel 3 centimeters. A single CPU core is about 5 millimeters wide, so we will run into these issues somewhere past 10 GHz.2. Switching delay. It's not enough to merely consider the time it takes for a signal to travel from one end to another. We also need to consider the time it takes for a logic gate within the CPU to switch from one state to another. As we increase clock speed, this can become an issue. Unfortunately, I'm not sure about the specifics, and cannot provide any numbers. Apparently, pumping more power into it can speed up switching, but this leads to both power consumption and heat dissipation issues. Also, more power means you need bulkier conduits capable of handling it without damage. Heat dissipation/power consumption. This is the big one. Quoting from Fuzzy Hair 2's answer. Recent processors are manufactured using CMOS technology. Every time there is a clock cycle, power is dissipated. Therefore, higher processor speeds means more heat dissipation. There's some lovely measurements at this Anantech forum thread, and they even derived a formula for the power consumption, which goes hand in hand with heat generated. We can visualize this in the following graph. As you can see, power consumption, and heat generated, rises extremely rapidly as the clock speed is increased past a certain point. This makes it impractical to boundlessly increase clock speed. The reason for the rapid increase in power usage is probably related to the switching delay. It's not enough to simply increase power proportional to the clock rate. The voltage must also be increased to maintain stability at higher clocks. This may not be completely correct. Feel free to point out corrections in a comment, or make an edit to this answer. More cores? So why more cores? Well, I can't answer that definitively. You'd have to ask the folks at Intel and AMD. But you can see above that, with modern CUS, at some point it becomes impractical to increase clock speed. Yes, multi-core also increases power required, and heat dissipation. But it neatly avoids the transmission time and switching delay issues. And, as you can see from the graph, you can easily double the number of cores in a modern CPU with the same thermal overhead as a 25% increase in clock speed. Some people have done it. The current overclocking world record is just shy of 9 GHz. But it is a significant engineering challenge to do so while keeping power consumption within acceptable bounds. The designers at some point decided that adding more cores to perform more work in parallel would provide a more effective boost to performance in most cases. That's where the economics come in. It was likely cheaper, less design time, less complicated to manufacture, to go the multi-core route. And it's easy to market. Who doesn't love the brand new octa-core chip? Of course, we know that multi-core is pretty useless when the software doesn't make use of it. There is a downside to multi-core. You need more physical space to put the extra core. However, CPU process sizes constantly shrink a lot, so there's plenty of space to put 2 copies of a previous design. The real trade-off is not being able to create larger, more complex, single cores. Then again, increasing core complexity is a bad thing from a design standpoint. More complexity equals more mistakes/bugs and manufacturing errors. We seem to have found a happy medium with efficient cores that are simple enough to not take too much space. We've already hit a limit with the number of cores we can fit on a single die at current process sizes. We might hit a limit of how far we can shrink things soon. So, what's next? Do we need more? That's difficult to answer, unfortunately. Anyone here a clairvoyant? Other ways to improve performance. So, we can increase the clock speed. And more cores have an additional disadvantage, namely, they only help when the software running on them can make use of them. So, what else can we do? How are modern CUS so much faster than older ones at the same clock speed? Clock speed is really only a very rough approximation of the internal workings of a CPU. Not all components of a CPU work at that speed, Some might operate once every 2 ticks, etc. What's more significant is the number of instructions you can execute per unit of time. This is a far better measure of just how much a single CPU core can accomplish. Some instructions, some will take 1 clock cycle, some will take 3. Division, for example, is considerably slower than addition. So, we could make a CPU perform better by increasing the number of instructions it can execute per second. How? Well, you could make an instruction more efficient. Maybe division now takes only 2 cycles. Then there's instruction pipelining. By breaking each instruction into multiple stages, it's possible to execute instructions in parallel, but each instruction still has a well-defined, sequential, order respective to the instructions before and after it, so it doesn't require software support like multi-core does. There is another way, more specialized instructions. We've seen things like which provide instructions to process large amounts of data at one time. There are new instruction sets constantly being introduced with similar goals. These, again, require software support and increased complexity of the hardware, but they provide a nice performance boost. Recently, there was ICE, which provides hardware-accelerated ICE encryption and decryption, far faster than a bunch of arithmetic implemented in software. One not without getting quite deep into theoretical quantum physics, anyway. 2 it might actually be lower, since electrical field propagation isn't quite as fast as the speed of light in a vacuum. Also, that's just for straight line distance. It's likely that there's at least one path that's considerably longer than a straight line.
Physics is physics. We can't keep packing more transistors into ever smaller spaces forever. At some point it gets so small that you deal with weird quantum crap. At some point we can't pack twice as many transistors in a year as we used to, which is what Moore's law is about. Raw clock speeds mean nothing. My old Pentium M was about half the clock speed of a contemporary desktop CPU, and yet in many respects faster. And modern systems are barely approaching the speeds of systems 10 years ago, and are clearly faster. Basically, just bumping up the clock speed does not give real performance gains in many cases. It may help in some single-threaded operations, but you're better off spending the design budget on better efficiency in terms of everything else. Multiple cores let you do 2 or more things at once, so you don't need to wait for one thing to finish for the next one. On the shorter term, you can simply pop 2 existing cores into the same package, for example with the Pentium Ds, and their MCM, which was a transitional design, and you have a system that's twice as fast. Most modern implementations do share things like a memory controller, of course. You can also build smarter in different ways. ARM does big little, having 4 weak low-power cores working alongside 4 more powerful cores, so you have the best of both worlds. Intel lets you down throttle for better power efficiency, or overclock specific cores for better single-thread performance. I remember AMD does something with modules. You can also move things like memory controllers, so you have lower latency, and I/O-related functions. The modern CPU has no North Bridge, as well as video, which is more important with laptops and our design. It makes more sense to do these things than just keep ramping up the clock speed. At some point more cores may not work, though cores have hundreds of cores. Multi-cores as such lets computers work smarter in all these ways.
Simple answer. The simplest answer to the question, why doesn't add more cores face the same physical limitations as make the CPU faster, is actually found within another part of your question. I would expect the conclusion to be therefore, we'll have to have bigger computers or run our programs on multiple computers. In essence,
Multiple cores is like having multiple computers on the same device. Complex answer. A core is the part of the computer that actually processes instructions, adding, multiplying, and ing, etc. A core can only execute a single instruction at one time. If you want your computer to be more powerful, there are two basic things you can do. Increase throughput, increase clock rate, decrease physical size, etc. Use more cores in the same computer. The physical limitations to number 1 are primarily the need to dump heat caused by the processing and the speed of an electron in the circuit. Once you split off some of those transistors to a separate core, you alleviate the heat issue to a large degree. There's an important limitation to number 2. You have to be able to split your problem up into multiple independent problems, and then combine the answer. On a modern personal computer, this isn't really a problem, as there are loads of independent problems all vying for computational time with the cores anyway. But when doing intensive computational problems, multiple cores only really help if the problem is amenable to concurrency.
Why doesn't add more cores face the same physical limitations as make the CPU faster? They do face the same physical limitations, but switching to multi-core design gives us some breathing space before we hit some of them. At the same time, other problems caused by those limitations arise, but they are easier to overcome. Fact 1. Power consumption and emitted heat grow faster than computational power. Pushing a CPU from 1 GHz to 2 GHz will push power consumption from 20 W to 80 W, same with dissipated heat. I just made up these numbers, but it's quite how it works. Fact 2. Buying second CPU and running both at 1 GHz would double your computational power. 2 CPUs running at 1 GHz could process same amount of data as one 2 GHz CPU, but each one would consume only 20 W of energy, that's 40 W in total. Profit: doubling CPU number instead of clock frequency saves us some energy, and we're not as close to the frequency barrier as before. Problem: you have to split the work between 2 CPUs and combine results later. If you can solve this problem in acceptable time and using less energy than you have just saved, then you've just profited thanks to using multiple CPUs. Now you just have to merge 2 CPUs into one dual-core CPU and you're home. This is beneficial because cores can share some parts of CPU, for example cache-related answer.
You can have